Today we're going to talk about reaction rates in chemical equilibrium. First we need to be able to explain equilibrium using reaction rates in the collision theory. So we know that atoms, ions, and molecules can form a chemical bond when they collide, provided that particles have enough kinetic energy. Particles lacking the necessary kinetic energy to react still collide, but they simply do not react because they bounce apart. The activation energy is the minimum energy needed for the colliding particles in order for them to react. There's four factors that affect the reaction rate: temperature, concentration, particle size, and of course a catalyst. Increasing temperature increases the number of particles that have enough kinetic energy to react when they collide. Concentration changes also affect reaction rates by cramming more particles into a fixed volume increases the collision frequency. Particle size affects reaction rates because the smaller the particle size, the larger the surface area for the given mass of the particles. Decreasing the particle size will increase the reaction rate because therefore more surface area is available. Catalyst is a substance that increases the reaction rate without actually being used up itself. So what does it actually do? It lowers the activation energy. So how does this apply to chemical equilibrium? Well, chemical equilibrium refers to the forward and reverse reaction taking place at the same rate. There's no net change in the actual amount of components of the system when the system's at equilibrium. It's a dynamic constant in motion type process that is reversible. Here's an example. We have the reaction going left to right is called the forward reaction, and we also have the reaction going right to left, which is called the reverse reaction. We can tell that this is a reversible reaction because we have the double arrow. There's two different types of equilibrium reactions. One's called a homogeneous reaction, where all the reactants and products have the same state of matter. As you can see here, all of them are gases. Heterogeneous reactions are when the reactants and products do not share the same state of matter. For example, we have a liquid here, and we have two aqueous. So that would be an example of a heterogeneous reaction. That's in equilibrium. Again, we know it's equilibrium because of the double arrows. Here's some practice. Please pause the video and tell me whether or not this is heterogeneous reaction or a homogeneous reaction. Okay, so here we go. We have two aqueuses on this side and a solid on this side. So this would be an example of a heterogeneous. This side we have a liquid, this side we have a gas. Again, this is a heterogeneous reaction. This side we have a solid, this side we have two aqueuses. This would be an example of a heterogeneous. We have a gas here, and a gas here. So that's an example of a homogeneous reaction. And same goes for the last one. Reactions at equilibrium have to do again with rate. So at this point here, this is where the reaction rate is the same. So we call that area of the curve to be an equilibrium. Going back here, this is where the concentrations are equal. A lot of kids confuse the fact that concentration have to be equal on both sides for it to be an equilibrium. However, this is not the case. We're talking about the rate. The rates have to be equal, the forward direction and the reverse direction. Factors affecting equilibrium are temperature, pressure, and concentrations change. This guy by the name of Chatelier came up with the principle that these three things will disturb equilibrium. So he said if a system is at equilibrium is disturbed, the system tends to shift in its equilibrium position to counter the effect of the disturbance. So the first change is called change in concentration. Okay, so what happens when there's an increase in a reactant or product, and what happens when there's a decrease in a reactant or product? Well, it's very simple. Okay, if we have an increase in a reactant, the stress then shifts the equilibrium forward because it wants to counter what's happening. If there's an increase in C or D or the products, there's a reverse shift in the equilibrium. Again, it wants to do the exact opposite to counter what's happening to the stress. If there's a decrease in the reactant, again, it wants to fill in that gap in order to counter the stress. So the reaction then, therefore, or the equilibrium then, therefore, shifts the reverse. If there's a decrease in the products, again, it's going to shift forward because, again, it wants to fill or counter what's actually happening. Changes in pressure only affect a system with unequal number of gaseous moles, okay, of the reactants and products. Okay, so here's the rule. If you decrease pressure, it shifts the reaction in the direction that produces a larger number of moles. Now, why is this true? Well, if you decrease pressure, what happens to the volume? The volume increases. So therefore, volume refers to space. If you have a larger space, you can have a larger number of things that occupy it. If you increase pressure, it shifts the reaction in the direction that produces the smaller number of moles. Again, this has to do with space and volume. If you increase pressure, volume decreases, therefore smaller numbers of moles of gas will be able to fit. Exothermic versus endothermic reactions. So here's a reaction. If we see heat on this side, we know it's exothermic because it's a product. We can also tell if a reaction is exothermic by having a negative delta H. Here's another type of reaction where heat is on the reactant side. And we know that this is a type of endothermic reaction because it's absorbing energy, and the delta H is a positive term. So, increases in temperature or increases in energy favor endothermic reactions in the forward direction. So if you are increasing this, it's going to shift to counter what's happening. A decrease in temperature favors exothermic reaction. Again, this is going down. Therefore, the reaction is going to shift in this direction.
Okay. All right.
Positive delta H, we know, again, are endothermic. Increase in temperature favors the forward reaction. Negative delta H, we know, is exothermic. An increase in temperature favors a reverse reaction. Let's get some practice here. If we take this example here, and we have brown gas, and it's in some ice, what do you predict is going to happen? Well, since ice is removing the heat, it's going to cause the equilibrium to shift in this direction. So over time, this gas right here should turn colorless. What does a catalyst actually do? So a catalyst will do nothing to change the equilibrium concentration. The only thing a catalyst will do, it will affect the rate of the approach. In other words, it'll get to equilibrium faster. Once a reaction has reached equilibrium, it remains at equilibrium until disturbed by some change in condition. These changes have to do with Chatellier's principle. We can either change the concentration, we can change the pressure, or we can change the temperature or the energy being applied to the reaction. Here's an example. So we know that we have an exothermic reaction because of negative delta H. Okay? We're going to apply some stresses at equilibrium, and we're going to predict where the equilibrium is going to shift to counter the stress. If we increase the temperature, we know that the shift will be to the reverse reaction because we have heat on this side. When we apply heat, it's going to counter by going the opposite direction. If we increase pressure, the reaction is going to go to the area where there's a smaller number of moles. Well, we have 2 on this side and 4 on this side, so it's going to shift in this direction towards the forward side. If we add a catalyst, we know that a catalyst will not change the equilibrium point. The only thing that it does is it reaches equilibrium at a faster rate. If we add H2, H2 is being increased on the reactant side, so it's going to push the equilibrium toward the forward reaction. And if we remove NH3, again it's going to counter it by filling that removal, causing the reaction to go forward. That's why Chatelier's principle has a qualitative approach to equilibrium.